All right, one thing I neglected to mention is Daniele is a new member of our Science Advisory Board, as is our next presenter. So Dr. John Buffington is a research geomorphologist with the U.S. Forest Service at the Rocky Mountain Research Station in Boise, Idaho. He graduated from the University of California, Berkeley in 1988 with a BA in geology, and from the University of Washington in 1995 and 1998 with MS and Ph.D. degrees in geomorphology. He was a Natural Research Council scholar from 1998 to 2000, a professor in the Center for Ecohydraulics Research at the University of Idaho from 2000 to 2004, editor of the Journal of Geophysical Research, Earth's Surface from 2015 to 2018, and has been an editorial board member of the Hydrological Processes since 2015. His research focuses on fluvial and hill slope geomorphology of mountain basins, biophysical interactions, and the effects of natural and anthropogenic disturbances on aquatic habitat. And he is the elder statesman on our Science Advisory Board, having served with us since 2010. So please welcome John Buffington.
Yeah, I guess I'm the old graybeard now. This presentation mixes both quantitative analyses and conceptual models. And the goal is to get us to think about how what the stability of channel morphology and aquatic habitat will be like in a changing climate, and what the implications are for management of the restoration reach. So a well-established paradigm in fluvial geomorphology is that the stable channel morphology represents a balance between the supply of water and the supply of sediment. And differences between those two are equilibrated by changes in channel slope and substrate size. And this conceptual model is used in both interpreting changes in natural rivers and for designing stream restoration projects. And while it's broadly understood that we need the whole hydrograph for ecological function of rivers, as Sarah demonstrated earlier, one thing that's frequently neglected in restoration design is that it is thinking about the stability of the channel morphology and the stability of the aquatic habitats as the discharge and sediment supply change over space and over time. And one important factor in that regard is hydroclimate. And in particular, the shape of the hydrograph. And this is not necessarily news for you, but the shape of the hydrograph fundamentally controls the variability of channel conditions in terms of the amount of work that can be done on the channel. So a snowmelt hydrograph is low amplitude, long wavelength. A rainfall hydrograph is flashier, and then a thunderstorm or a monsoonal hydrograph is even flashier. And some work done in the 90s by John Pitlick looking at these sorts of different hydroclimates shows the range of work that can be done in terms of differing sizes of floods from the 2-year to 100-year normalized by the 2-year flood. So if we look at the ratio of the 100-year flood to the 2-year flood, in a snowmelt environment, it's not very different. It's only about a value of 2. In a frontal rainfall system, because it's flashier, the ratio is higher, it's almost 5. And then in a thunderstorm system, it's 9. So this has implications for the amount of work that can be done in the channel. And so what the hypothesis is, different hydroclimates are more or less volatile in terms of changes in channel morphology and changes in aquatic habitat. In order to formalize this conceptual model, we can use a regime diagram, which on the x-axis plots the dimensionless discharge and the y-axis the dimensionless bedload transport rate. And in an equilibrium system, the transport rate is equal to the sediment supply. So the x and y-axis are the supply of water and the supply of sediment. And then the equations for those are shown over here. And the important thing about that is that there are characteristics of the channel embedded in these equations that allow us to make predictions, which are shown by these contours of stable channel morphology. So for a given discharge and a given sediment supply, we can predict what the stable channel slope is, the stable depth over grain size, and then the stable or the value of channel mobility in terms of the bed substrate. So the shear stress normalized by the critical shear stress. So we can go from this conceptual model to very quantitative predictions. For a given discharge and a given sediment supply, we can predict the stable morphology and think about how the channel might change for an increase in supply or discharge or some combination of the two. We can also take this same regime framework and populate it with data from reach scale morphologies. So thinking about steep boulder-bedded cascade or step pool channels, cobble-bedded plain bed channels, gravel pool riffle channels, and braided channels. So each of those channel types are represented here in different colors. And what you see is there's a lot of overlap in the diagram, but we can identify fields or domains for each of these channel types. So beyond thinking about what the stable grain size or slope or depth of the channel is, we can also think about what the stable morphology might be. Okay, so armed with this framework, now we can answer this question of how variable are channels in different hydroclimates. In the first case, we'll look at, we'll consider a nice meandering gravel bed channel, and this particular channel for its discharge and bedload transport rate might plot in this particular spot in the diagram. And then we ask for bankful conditions. And then we ask the question, how variable do we expect this channel to be in different hydroclimates? So the first case is a snowmelt environment. And what this shows is the range of conditions we might expect from the 2-year flood, which is something like bankful, up to the 100-year flood. And there's two boundary conditions here that define this blue field, which is our sort of playing field of expected variability. And the lower bound is assuming a constant slope, and the upper bound is assuming a constant depth over grain size. And in the short term, we can't change the valley slope very much. So most of our changes in condition, we expect to hug this slope line. And based on the data from John Pitlick and the relative size of floods in a snowmelt environment, we don't expect very much variability in channel conditions. But that result changes when we think about a flashier rainfall system or a monsoonal system. So the response potential and the temporal variability of channel conditions likely vary with hydroclimate. Snowmelt channels are relatively stable across floods of different magnitude, while rainfall channels are highly variable and less stable. We can also use this framework to start gaming what-if scenarios for climate change. So if we think again about this snowmelt system and ask the question, what's the channel going to look like if that snowmelt, if the snowpack is reduced by half? We would predict a shift in the channel characteristics, but the same range of variability in channel, relative variability in channel conditions, because we're still in the same snowmelt environment. If we now add a mixed rain and snow environment, we might predict a broader range of channel characteristics. So this gives us a way to move beyond some of these conceptual models and make some very specific predictions. But this framework is fairly simple because we're dealing with discharge and sediment supply, and there are a lot of other factors that matter that modulate these potential responses. And the first is process domains, where we are in the stream network, whether we're close to the tips of the network coupled to hill slopes and debris flows, if we're in the midsection of the network where we have confined steep reaches, or down in low gradient floodplain valleys. Each of these places have different degrees of freedom in response to those changes in discharge and sediment supply in different hydroclimates. So we can think about different disturbance regimes with different frequencies and magnitudes in each of these places, and then different ranges of channel conditions that go along with those different disturbance regimes. The most important one, which is particularly relevant on the Trinity, is confinement. In an unconfined alluvial valley, if we have an increase in flood size, most of that is dissipated by overbank floods, whereas confined channels, that higher flow is directly translated to the bed in terms of a higher shear stress and higher scour potential. The mobility of the sediment also matters. This is a plot of the bankful shield stress. So this is the shear stress normalized by the grain size as a function of channel slope for different channel types, sand-bedded rivers, meandering, pool rift, whole plain bed, step pool, and cascade. And the sand-bedded rivers, because of their particle sizes, they're really mobile, high sediment transport rates. The coarser grain channels exhibit a systematic change in mobility as a function of slope, which is more evident in this plot, where we're showing the bankful shear stress divided by the critical shear stress. And we expect a higher mobility as you move from pool riffle up through cascade channels, at least in terms of the median grain size, not the boulders that are forming the structural elements in step pool and cascade channels. So the point of this is just that any change in discharge or sediment supply may have differences in response based on differences in bed mobility across these channels. Another really important factor in mountain basins is debris flows. So here we're thinking about tributary basins that are more coupled to hill slopes, and in particular, in a changing climate, the frequency and magnitude of wildfire. So this is an example from rivers in the Rocky Mountains in Idaho. After a wildfire, the landscape is denuded, you have hydrophobic soils, and there's a window of about 10 to 20 years where this landscape is prone to extreme erosional events. And the trigger in this place is you get localized intense thunderstorms that cause rapid runoff that initially starts off as a clear water flow, picks up more sediment, becomes hyper-concentrated, picks up more sediment, and becomes a debris flow. And those debris flows traverse the entire tributary down through the middle segments and then deposit these enormous fans in the main stem river. So the tributary comes in here on the left, the main stem is flowing from the bottom to the top, and this circle shows a bulldozer for scale. There are direct impacts of the tributary fans on the hydraulics, channel units, and associated habitats. So here's a cartoon of this fan. The fan partially or completely blocks the river for some period. It creates a backwater pool, a dammed lake, which is great habitat for juvenile fish. And over time, the main stem erodes this fan, and that material is carried downstream. It's a mixture of sediment and wood. So this is a proximal effect, but then there's a distal effect of that material moving downstream. In some cases, the movement of sediment and wood completely overwhelms the previous river in the main stem. And to look at this, we did a study looking at how this movement of sediment influences spawning habitat for salmonids. And so this figure shows median grain size as a function of distance. The gray band is a range of sizes that are suitable for spawning for different, a range of salmon that are in this basin. And the black line shows you the availability of, or it tracks grain size and the availability of spawning gravels in one of these steep confined mountain rivers. And what you see is in this environment, because the channel is steep, there are only a few places where you've got suitable spawning gravels. Now, after these debris flow events, we had 3 tributary debris flows deposit these enormous fans in the river, and at each location, because the size of the sediment was smaller than what was in the river, it produced spawning gravels at each of the fans. And then that material moves downstream over time. So if you look at this oval, you can see how it's routed downstream through the network, and you have these patches of spawning gravels moving downstream. So this is an example where debris flows are beneficial to the fish, delivering spawning gravels in a place that otherwise might not have them. And that's a little bit different than the example that Seth showed yesterday, where you had a fine grain fan that delivered fine sediment to an otherwise suitable habitat and smothered those habitats. So it can be beneficial or it can be detrimental depending on the local conditions and also the characteristics of what's being supplied from these debris flows. Now, if we look within the tributary basin to look what's happening there, the debris flows either scour the channel to bedrock or they leave these massive deposits in the valley that So this upper arrow shows the initial deposit of the debris flow that completely blanketed the existing channel and reset the whole system. Subsequent clearwater floods incise into that deposit and develop a fluvial morphology. So what we've got going on in these systems is this interaction between the debris flows and the fluvial processes. And if we look at the data from these channels, so we surveyed these channels, and they're typically plain bed, step pool, or cascade channels. And in a normal fluvial environment, these are data from a environment that's not influenced by debris flows, but we see that those morphologies sort of dovetail with one another in terms of what's happening in the debris flow environment and what's happening in the alluvial channels. So these lavender symbols are for cascade, and the blue are for step pool, and the green are for plain bed. So the fluvial systems line up with one another, but in the tributary basins, they're influenced by these debris flow processes that are delivering sediment and the boulders that are the structural elements for these steep channel types. So the point of this is that in addition to thinking about the supply of water and sediment, we also have to consider these other geomorphic processes that are happening in certain places in the basin. Okay, so there are a variety of biophysical controls that modulate any expected changes in channel morphology and aquatic habitat due to changes in discharge and sediment supply with hydroclimate. And these things include lithology, the shape and slope of the basin, the drainage density and network structure, the vegetation type, wildfire history, and then land use. And land use can be logging, mining, dams, and diversions. There's a host of things that modulate any sort of response that we might expect. And you know this well for the Trinity. All of these things are in play. So if we go back to this regime diagram and think about different characteristic reach morphologies, like a pool riffle channel in this red field and a plain bed channel in this green field, we might expect that over time we would have a distribution of channel characteristics or channel conditions. So there might be a mean value and then some variance about that as the channel experiences different sized floods and different sediment supply. But there's also an interesting situation of channels that are on the border between two different morphologies. And those channels can be transitional or more dynamic. So they're sort of at a tipping point between two different morphologies. And there's a great example of this at Uvis Creek near Gilroy. There was a stream restoration project that you guys probably know about where they used a 2-year flow that's approximating the bankful flow, and for that flow designed this nice idyllic meandering pool riffle channel. But during a subsequent small flood event, a 5-year event, the channel completely unraveled. And this is one of these places in the landscape that's a tipping point. So if we look at this in a regime diagram, this one's a little bit different. It's particle size versus dimensionless stream power, and it's meant to distinguish different channel patterns, so braided versus meandering. And this lower blue point is the bankful design for Uvis Creek, and it fits squarely in the meandering field. So the design seems quite appropriate, but what they didn't consider is how volatile this channel is with changes in discharge. Here's the prediction for the 5-year flood, and it rapidly moves towards this boundary between the meandering and braided channels, and in reality, it reverted to this braided morphology. So the point of this is that even if we can predict that we think the stable morphology in the long term is a pool riffle or a plain bed channel, they're not all equally stable, in the sense that there are some that are highly volatile and maybe in these tipping points. Okay, so that's channel morphology. Let's think about stability of aquatic habitats, and in particular, the stability of eggs that are buried in the stream bed gravels by salmonids, so red building, and how vulnerable those are to changes in hydrologic regime and changes in scour. So we'll consider this same pool riffle channel, and we're going to think about scour of bull trout eggs. Bull trout are relatively small-bodied salmonids, so they're just bearing their eggs to a depth of about 10 centimeters in this environment. And we use a empirical scour equation, which is a function of particle mobility. So this is the applied shear stress normalized by the critical value. From that, we can look at the probability of exceeding some specified scour depth, in this case, 10 centimeters for bull trout. And we're going to ask what's the risk of scour in different hydroclimates. So this figure shows the probability of scour, or the proportion of the bed that would scour, as a function of flood size in 3 different hydroclimates: snowmelt, rainfall, and thunderstorm. And what we see is for floods of 10 years or greater, there's a systematic difference in response. The snowmelt environments have relatively less scour compared to the rainfall and the frontal systems. So this fits again with what we know about the size of the hydrographs and the probability of scour. Now, this is a prediction for just one place in the landscape. We can do the same prediction across an entire watershed using digital elevation models. And this is some work that Jamie Good did, where we're looking at this prediction in the Middle Fork Salmon River, which is the largest unregulated basin in the lower 48 states, over 10,000 kilometers of stream. And she used a global climate model that was downscaled to predict changes in discharge and then consequent changes in scour potential. And we look at 4 different fish: Chinook, steelhead, migratory bull trout, and resident bull trout for historic conditions and predictions in the 2040s and 2080s. Blue colors are relatively low probability of scour, and then hotter colors are increased probability. And what you see is that the bull trout are at a higher risk of scour compared to the Chinook and steelhead. Oh, and I should mention, in historic conditions, there's relatively low probability of scour for all the fish. They're adjusted to the historic conditions. And the reasons that the bull trout are more at risk is because they're smaller fish, they're burying their eggs to shallower depths, and they're also spawning in confined and semi-confined places or stream valleys, so that when higher flows are predicted, those are directly translated to the bed in terms of a higher scour potential. In contrast, the Chinook and steelhead are spawning in lower gradient unconfined valleys with nice floodplains. Any change in flow is dissipated across the floodplain, and they're bigger fish. They're burying their depths they're burying their eggs to larger depths. So the moral of the story is, even within a given basin, for a given predicted change in hydroclimate, that climate change will play out differently for different fish species. So there can be losers and winners. Okay, so to summarize this. In terms of hydroclimate, we expect the stability of channel morphology and aquatic habitat to be influenced by hydroclimate and an associated discharge variation. Snowmelt channels are expected to be relatively stable across floods of different magnitude, while rainfall channels should be more variable and less stable. Scour potential and risk to benthic animals varies with the hydrologic regime, particularly for large floods. So conceptually, we know all this, but frequently it's not considered in restoration designs, again, in terms of the spatial and temporal variability of floods and sediment supply. Typically in restoration designs, we focus on things like the mean long-term conditions, so concepts of equilibrium, or the bankful or effective discharge paradigms, or we think about evolutionary trajectories, so stream succession is envisioned by a variety of different authors with different models, ranging from Stan Shum in the 80s to recent work by Kluwer and Thorne on stage 0 channels. So we need to formally include this discharge variability in our representation of fluvial processes, biophysical condition, and restoration design. And I think that's central for assessing the potential effects of human disturbances on the landscape. So not just considering the seasonal variability of the hydrograph, but how the channel will respond to a sequence and history of different floods and sediment supply events. In terms of climate change, the effects depend on the specific changes in hydrology that occur within a given basin, but the transitional environments, those changing from snowmelt to more mixed rain and snow, or even a predominance of rain will increase the potential variability of channel conditions. And that in turn will produce a more volatile, less stable aquatic environment. But those impacts are species specific and location specific within the basin, as I showed for the Middle Fork salmon. So again, there may be losers and winners depending on species size, phenology, and habitat preference. So what does all this mean for the Trinity? These are some initial ideas I have, and I'd like to encourage discussion with you guys to see what you've been thinking about climate change. From my initial thoughts, I think there's good news and bad news. The first is what Sarah talked about earlier. You guys are in luck because you have an allocated flow by water year type, and you have the ability to shape that hydrograph, which makes the restoration reach relatively immune to climate-related changes in the timing and magnitude of flow occurring above the dams. So you have control over what's happening in the upper basin. But you also have uncontrolled tributary basins. So in terms of future shaping for winter flows and overall synchrony with tributaries like Seth talked about yesterday, you may need to consider climate-related changes that are occurring in those tributaries in terms of how you shape the hydrograph and whether you want to bring the restoration reach hydrograph into synchrony with those tributaries if the changes are beneficial or potentially detrimental. So it's something that, I think you should cautiously evaluate. I think synchrony is good, but it needs to be in the context of whether it's a good change or not. Potential bad news, again, Sarah talked about this. There's a potential for a new normal due to changes in the occurrence of dry, normal, and wet years, and extremely wet and extremely dry. The normal may not be the normal anymore. You may have a new normal. And if that's the case, then you may need to rethink channel dimensions and substrate size for naturally functioning rivers. So something to consider in future designs, and maybe something to consider in terms of a retrospective, going back to completed designs and asking the question, are they functioning the way we designed them for under this new normal? And we expect with climate change, we're going to see more extreme events, more dry years, and more wet years, but the whole system will be trending to some new state. And that will vary regionally, but in many places in the West, it's towards a drier environment. So I'll stop there and would appreciate conversations with the rest of the scientists and program partners about what you may have been thinking about this.
Hi, John, thanks for the presentation. And thanks for ending your presentation on climate change. Something that I've thought a lot about, and I think others have too, is the snowmelt component of our hydrograph. We have the ability to preserve that regardless of whether we actually have a snowpack or not. But of course, looking forward to the future, who knows what's going to happen generations from now with the dams that are there? Are we setting up the system to a eventual outcome that we're not able to support if we do that? If we lose our snowpack, what justification do we have for mimicking it?
Right. You could essentially create a relic system of what it used to look like. Let's say recreating that snowpack that no longer exists, that snow runoff. And that could be okay if that creates an optimal habitat. It would be artificial, but maybe it would be very productive. Or you can mimic the changes in climate that are occurring and the changes in flow, and that may also be productive too. It's something to explore. But I guess I view it as an opportunity because you have a water allocation and you can shape the flow. You have a lot of opportunity.
I agree. Thank you.